Thank you for joining me for this video. I am Mr. Ish. I hope everyone's doing well. We're looking here at just a single reaction in this video. What is the end product of it? We have what is over here is cyclohexane ring, from which are stemming two carbonyl groups. And these are ketones. If you were to number this, you're looking here at 1, this is 2, this is 3. And then you can number it. You have 1, 3. Then you have cyclohexadione. And that's exactly what it is. 1, 3. 1 and 3, cyclohexane coming from right here, and then dione meaning two carbonyl groups, and they are ketones. That's what it is. We are reacting it with this single mole of methylbromide, and we obviously have this LDA and THF. This right here is your solution medium, but this right here is a very strong base. Lithium diisopropyl amide. It's strong enough to pluck out a hydrogen from a carbon atom. This has everything to do with the acidity of your alpha hydrogen, which is found on the alpha carbon. What is your alpha carbon? Well, you have multiple alpha carbons over here. So what we need to do is determine where the reaction will occur, on which alpha carbon will that hydrogen be plucked off. If I were to draw this in a non-abbreviated way, this is what I have. I have over here a hydrogen and a hydrogen. You know, you have the two carbonyl groups over here. Then I have the hydrogen here and hydrogen here. I have a hydrogen, hydrogen, and hydrogen. Because you know the valence of carbon is 4. There will be 4 items stemming, unless you have something over here, a double bond with an oxygen, and you already have met the valence. So that's what it is. This right here is my carbonyl carbon. Here's my carbonyl carbon. Then the one carbon away is your alpha carbon. So this right here is your alpha carbon. Right here, this here is an alpha carbon, and this right here is alpha carbon. We can designate it better in a more clear way using an asterisk. Here's my alpha carbon, here's my alpha carbon, here's my alpha carbon, which means you have 1, 2, 3, 4, 5, 6 alpha hydrogens. And which of these alpha hydrogens are going to be plucked off? Only a single one will be plucked off because we're doing 1 mole over here, but which of these hydrogens will get plucked off? Obviously, the most acidic alpha hydrogen will get plucked off. And that would be the one right here between the two carbonyl groups. The reason being, if you're looking at your carbonyl group, you have what you're looking at is something like this. Here's your one hydrogen, here's your other hydrogen. The reason why any of these is the most acidic versus a hydrogen over here and a hydrogen over here, these are less acidic, but this right here is most acidic because of the effect of having two carbonyl groups sandwiching it in between. You know what you have over here are two carbonyl groups. They're electronegative. They're sucking electrons towards the oxygen, and hence it's sucking all of the electron density from this carbon this way and in the other way, and it's making these more acidic. The reason why the adjacent hydrogens on the alpha carbons are not as acidic is because they're not sandwiched between two ketone groups. Here you have two carbonyl groups, and these two hydrogens are sandwiched in between. When you pluck off this hydrogen, you have resonance stabilization, better resonance stabilization, which you would not see anywhere else. And I can show it for you. If you pluck off one hydrogen, you've developed a carbanion, a carbon with a negative charge, and then it can resonate between either of these two. You can have a resonance structure develop, and I will show it to you. You have one which is something like this, and then obviously you can go in this other direction, and we will show you the other one. You will have, let's complete. There's a negative charge here and there's a negative charge here. These are your 3 resonance structures. You can resonate either towards the left, towards the right, but you have that resonance structure for this alpha carbon being the best. These alpha carbons here on the side are not as good because this is sandwiched between two ketone groups, two carbonyl groups. That functional group on either side plays a big role in making these hydrogens very acidic. Given that as your fact, let's answer the question. When you react this with a single mole of these reactants and methyl bromide, what you will see as your intermediate, it will be this. And let's demonstrate it for you. You still have your cyclohexane ring, but you have one hydrogen which I'm not drawing, and then you'll have your carbanion develop right over here, because the hydrogen which was over here, one of these hydrogens got plucked off, and it's arbitrary which one you choose. I'm picking this one, it got plucked away. I'm not showing you the other hydrogen, but it would be here. When you react with the methyl bromide, the methyl group will attach over here. The end result of this reaction is you're developing a carbon-carbon bond. So your end result is this. Your final product is going to be exactly what I'm showing you right over here. A methyl group, CH3 plus HBr. This bromine and one of these hydrogens will give you the HBr. these items here will be regenerated in the reaction. That's your answer. How will we identify this in terms of appropriate nomenclature? Well, we know this right as 1,3-cyclohexane dione or cyclohexadione, either way you want to say it. But this right here, you can say it as will be, if this is 1, that's 2, this is 3, you can say 2-methyl 1,3-cyclohexadione. Some would say cyclohexane dione to bring the whole hexane, some will say hexadione. But this right here is good. 2-methyl 1,3-cyclohexadione, that's your product plus HBr. Thank you for watching.